Come on, man. Okay, we're back. I'm changing let's get rid of my own voice. But due to some internet, we ended up getting cut out for a little bit. So we're coming back. Restart. So we're getting back into, oh, yeah, and just you gotta run these a little out of order so that they work. So PLT has a scatter, but yeah, it doesn't have the same option. Like I would have to change how I define hue and all that. So we'll leave it as SNS because it does work this way. Cool. One thing that I wanted to say about this problem is that, all right, so we'll energy. Make sure that the data that we're trying to like subset, like grab out of this, so that it actually exists. So if I try to just grab Africa, it'll show me, it'll show me all of the continent of Africa, how much energy it's used over the last 50 years, 65, anyway. And what I'm trying to do is United States. And again, so it works here. I could have also said code equals USA, and it gives me the same data set, but make sure that this does exist first when you're grabbing it. So US equals that, and then let's say energy of energy bracket entity is Europe. Europe doesn't have a code because there is no, it's not talking about one country, it's adding up all the countries that are part of Europe. So I can't use that code, but I can type in the word Europe for that entity. And now I can say EU is that value. And now I've got like two data sets. And the assumption here is that energy consumption is a function of time. That's what, when we're doing this fit, what we're saying is that there is noise in the data, but a lot of that can be taken care of by saying like, okay, it is some function of time. Because if I just look at a histogram of US primary energy consumption, it looks like there's more often more energy. And yeah, it does not look random. Like it's not like looking at the any other examples. Yeah, if we come back to like part one, when we were looking at like the IBU and the ABV values, so like alcohol by volume, and these haven't run yet. so I have to run them all. But it doesn't have like these kind of random values. Like it doesn't have a noticeable norm or anything. So there's something going on. So one way that we can take care of this is say like, all right, it is a function of time. So let's look at and what do we want to call that? Is it date or year? There we go, year. And if I look at the year versus energy consumption, there's something weird happening in the 80s. 80s were a weird time, I guess. And then something again, 2010s were a weird time. But there definitely seems to be some kind of like, as time goes on, energy use is changing. And I can copy this, compare that to EU. So now I've got US and EU. For a little bit, EU was using more, and then US continued to increase. Now EU is doing a little better. And this was another one I noticed some strange things. So let's see what ChatGPT has in store for us. Is it going to ask me for this lin regress? So that's where it's coming from. So SciPy stats lin regress. It works. Oh my god! Now I gotta upload this thing from my computer. Let's see if I have it. What is the name of it? Primary. I don't know if I've downloaded it recently. OP. No, so I'll have to go into here, back up one, come down to primary energy consumption and download it. And now I can upload it. Primary energy consumption, give it to ChatGPT. Now it's got all this new data to work with. And it's interesting. Why? Oh, it's probably maybe it's running out of tokens. Let's make a new chat. Oh, interesting. Yeah, it's still having trouble. I don't know why it's having trouble. Oh, I've reached my analysis limits. Can I change to... I thought there was a way... Oh, geez, no, I don't want that. Search web, view tools. I wanted to make it just a less... So I ran out of, I thought I could have won't let me change. So it's kicking me out. It's telling me that I've asked too many questions lately. All right, well, I can do it without you, ChatGPT. So ChatGPT wanted me to use so lin regress Python the SciPy linear regress, SciPy stats linear regress. This one, it works. Has some good stuff. If I want to use like a more advanced linear regression tool, I don't think I would jump into linear regress. What I would do is SciPy, stats models. If I want to do linear regression and I want to get more information about my linear regression model, I would use this or OLS, like linear regression from stats models, because it's going to give me a whole bunch of extra stuff that I can use to kind of showcase that I've done the analysis correctly, that the model is fitting correctly. It gives me my R squared, F stats, and all sorts of like good extra stuff, rather than the SciPy stats. It works, but this one's a little more in depth. And you can scroll down, and here I just want to grab, well, here it's showing us like how we can set it up. We could say create this sm.ols model, create a model fit, and then give me the summary of that model. But this is a lot of extra information that I don't really need. Really, I just want a best fit line, and I don't need a lot of the extra stats in there. So XUS is going to be US year dot values. YUS is US primary energy dot values give it my x coordinates, y coordinates, tell it that I want a first order fit, and I get a slope and an intercept. And the higher order, so if I say 5, it's going to give me all of the higher order polynomial constants here. So polyfit is a great way for like first order fit and any kind of polynomial fits. So I'll call this my like coefficients for US is this. And now I can say plot XUS NP dot polyval. So I can use polyval to take those coefficients, plug them right in, and make it at the same x coordinates. And now I've got this straight line fit for US. I'll do the same thing, and let's make it a blue curve to kind of match. And let's make this one also blue, so they both match each other, US and US. And then we'll say that this one is red, and we'll grab all those. I'm just using this control click so I can change all these US values to EU all at the same time. And I want this one to be red. So now I've got EU energy, US energy, and I have a best fit for both of those. And then the next step is splitting that up into, like, considering this something like before 1980 and after 1980 as two different data sets, and doing the same kind of analysis there. And yeah, for a quick best fit line, I think polyfit and polyval is a much easier to read and easier to interpret. But if you want something much more, if you want a lot more data about your fit, then go with stats models. So if you're using ChatGPT and it hasn't kicked you out for using it too much, then specifically tell it like, hey, use stats models for the least square regression, and hopefully it'll, if it hasn't kicked you out already. Anyway. Well, now it seems like it's moving along. Now it does seem like it's working. Slowly, surely, coming along. Oh yeah, and I saw the same kind of like print statement too. And it works. Predict year 2025. Yeah, something like this. And the nice part about using that stats model, so paste this in, try running that code, see what we get. Big old error. Oh my god. Path to your CSV file. Oh, I want primary energy consumption. Energy consumption. All right, let's see. What is your... This is supposed to say primary energy. This is supposed to be primary energy. Oh my god, it's still... But it is giving me, it's starting to give me all this extra data that I was trying to say is there. And it's, the main problem is coming up in that it didn't know. So all of these are supposed to say let's see if that works. All right, so it's doing the analysis, but it's not actually showing what the results are. And that's a huge problem. I don't know why. Did I say split it the year 2000? $2000's fine. It's kind of a weird time to split the data, but it works. But definitely, if you're making a fit, you definitely need to show the fit and the data. That's like the bare minimum for what needs to happen if you're trying to say like, hey, look at all these great statistics about how good my fit is. That doesn't mean anything unless you actually show, here's the data, here's the best fit. So we already, like we have a way to plot like this data. And model Europe after. I'm trying to figure out USA before and I want to just use this thing. Predict 1, why is it? See, it gets a little confusing here. Let's try that. Okay. So it started to work because it shows me before the year 2000, that data. And now I can copy all this, change this to after. Oh, and I also need to change the USA before to USA after model. And there we go. Now I've got a before and after prediction. And this is one of the reasons that I was saying the year 2000 seems kind of weird, because from 2000 to 2020, on average, it looks like it's decreasing, but I highly doubt that now, 5 years later, we're actually continuing to decrease our energy. So if it was me, I would say, like rather than saying 2020, maybe 1990. And now I've got this split here. It's going to be, no matter where I split it, it's going to be discontinuous. It's not so wherever the split happens, it's just considering these two data sets independently. Yeah. And in here, one of the main tripping points is that we're trying to work with log scales here. And Moore's law is specifically talking about like doubling every 2 years. So if you want, like, it might make sense to use a log2 function to like put the data into a log base 2 to see how many years it takes to double. So I could say NP log fit of xi, log 2 of tc, and 1. And what I get is that my slope on a log base 2 plot is about 1/2 with an intercept of this like -9. Intercept we don't really care about. So we'll say this is like my fit is this. Xi, tc, we'll put all these as like circles. Xi, and then if I try to just put, if I could actually remember, if I try to just put my plot back onto here, it's not going to look quite right. So let me put it back onto that semi-log y. And it's still, I'm way down here because I was doing this fit on a log base 2 scale. So I need to get my fit back into that 2 to the something. Or if I did just regular log, then this would be np.exp of that thing. And the nice part about putting it into that log 2 is that now I have my fit bracket 0 is a direct comparison and like times 2. It's saying that every 2 years, number of transistors was 96.9% of what it used to be. So it's almost doubled versus Moore's law would say that on this log base 2 scale that this would be exactly 1, that every 2 years you're 100% bigger. So now I have a way of like directly comparing if I want to do like log 2, if you want to use log 2. Cool. Then coming into these are both in the same. Let's split those up. There we go. All right, so the main thing that happened here that I noticed was that people were either only calculating one x, so let's do this, from numpy.random import default RNG equals default RNG. I'm going to use a seed value of 42, so if you're trying to recreate what I get, you'll always get the same numbers, at least if it's in the same order. And we want to make 100 needles, or is it random, or is it, yeah, random. And actually I'm going to turn this into n and say n is 100 number of needles times 2 times pi. So I'm going to take the random, I always get random numbers 0 to 1. I'm going to multiply them by 2 pi, and now it becomes 0 to 2 pi. So my first one end of my needle, I'll call it like x1, is x plus np dot cosine of theta. The other one is x minus np dot cosine of theta. And I'm just going to make 10 needles to start, so I can look at x1. I want to put these like side by side, like this. All right, so I made 10 needles. Each of them have a random x location. So the middle of the needle is in a random spot between 0 and 1. The left side is going to depend on the angle and that length of the needle. So in this case, for case 1, for that first needle, it landed, the x1 is 0.1, x2 is 1.5. So it's to the right side of 0. So it does not cross the 0. Then when I look at this next one, x1 is 1.3, but x2 is over in negative 0.5. So this means that theta was something more than 90 degrees, and this is crossing my 0 line. So this one would count. That would be like one of the needles crossing 0. Then this one is not crossing, this one is not crossing, here it is crossing, not crossing, this is crossing, is crossing, is crossing, and is crossing. So in this case, I have 1, 2, 3, 4, 5, 6. So I have 6 out of 10 crossing here, crossing that. So 6 over 10 is 0.6. And pi is going to be so even with just these 10 needles, I get a value of pi of 3.3, which is pretty close to the actual value of 3.14. And it's a little cumbersome to like add these up by hand like that. So when you have 100 needles, it doesn't really make sense to like count them up one by one. But in doing this, what I could notice, you can approach this lots of different ways. One is looking at like, is the min, so I could arrange these like minimum, maximum, and then see is the min less than 0 and max more than. I could look at just the signs and add up the signs of each one of those and see if the sign, like if this sign is 1, that sign is 1. If I add them up, then it adds up to 2. This is 1, this is -1. So if I add them up, it adds up to 0. So I could look for all the zeros that way. Yeah, different ways of doing it. But let's stick to, like I had suggested this logical AND operation. So let's do some logical AND stuff. We'll say x1 np dot logical a and b of x1 more than, or wait, we'll say less than 0, x2 more than 0. And let's just comment out that one. So in this case, I get 3, which is half of what I just counted. And the reason for that is that I'm only counting the times when x1 is less than 0. So what I could do is daisy chain a logical AND and a logical OR. So now it's going to look for this case or this case. And now I get 6 values. And if I bump this up to 100, I get 73. 73 over 100 is now 2.7. So it got a little bit worse. That's okay. If I keep bumping it up, I get 640. If you keep increasing your the number of needles that you're using in the analysis, then you'll keep getting better approximations for pi here. Yeah, so that was the one thing that I noticed is that if you're trying to say like, all right, this side and that side, one's less than, one's more than, you either have to rearrange them to look at a min and max, or create like an or statement of saying like either this is true or that's true and count both of them. Then in this Monte Carlo buckling method, really we're just trying to grab this function. So let me put this one right in here. So I'm going to say R is RNG dot normal location. Oh, I think it's location equals R mean, scale equals or is it norm? Let's double check. Yeah, location, scale, and size. Okay, just had to double check. Scale is our standard deviation. Oh. Size equals n. So n just has that default value of 100. And I could put some default values in here too if I want. I think this is 0.01, sorry. And this is we'll say L is 5. Now I can calculate that P critical, which is np.pi cubed times E times R. R is now a random variable, so it's creating 100 or however many rods I'm creating. But raise that to the 4th power, divide by 16, divide by L squared. And I should set that equal. And I'll say this mean buckle load is the mean of P critical, and standard deviation buckle load is standard deviation of P critical. And now when I say that Monte Carlo buckle, it's going to give me 164 and 61. Each time I run this, it'll be a little different because it is creating random radii. And this is just telling me about the rods themselves, like how strong they are. So on average, the buckling load is 175 newtons. The changes in that is plus or minus 71 newtons if I'm just describing like that 66% of our, here coming back up to not here. Well, let's just go back into describing data. If I'm thinking about like the quartiles of this function, or maybe not. Well, here's the quartiles. Anyway. Oh, I was all the way down here. Yeah. So one thing that I could do is say like, all right, I also want to look at that P critical. So we'll say mean, standard deviation, PCR is all that. And when I look at this, it's not a normal distribution. So again, Monte Carlo, bigger is better. Let's make like 10,000 different rods and see how that looks. And we have 10,000, so let's make it 50 bins. And I can see here, it's not really a normal distribution because I'm taking a normally distributed R and bringing it to, raising it to the 4th power. So it's not really normal, but I could kind of squint my eyes and say like, well, maybe it's not skewed. So I could say the mean minus 2 standard deviations is going to be that lower limit, like where I want to say, compare that to the actual load that the structure has. And the structure here is, it's holding a 1,000 kilogram structure with 100 steel rods. So each rod is holding 10 kilograms, or comparing it to our critical, 98.1 newtons. So every rod is holding 98.1 newtons. So let's print, and I just want to get rid of that. Mean minus 2 times S, and so right now, if I take the mean, that mean 165 minus that 70 and 70, the 97.5%, so 33 newtons down here is describing like that 97.5% are bigger than 33. But what I want is, I want this to be 98.1. So I could say, so let's make L 2 meters. And now it's too big. Now it's too short, because this is saying 205 compared to that 98.1. So let's make it like 3. Now it's getting a little bit closer. 84, maybe like 3.5. Oh. 2.9, a little shorter. So 99, at least with this like mean and 2 standard deviations that way. But I also have this P critical, so I could say how many of those P criticals are less than 98.1. And in this case, it's 5 divided by 10,000. So this is making a really an overly careful, like a overly conservative assessment of this, because most of the values are going to be above, like there's a skew. It's skewing to the right in this case. So instead, what if I said like, all right, well, what about 4? And now I'm at that like around 2.5%, right? That if it's 4 meters, then the number of these rods that are less than that applied 98.1 is only 2.3%. So that's that's a little bit better, right? And 4.3 is a little too big, not conservative enough. And 4.1 is a little, again, a little too much, like 2.67. It'll change each time. 2.8, but still it's around that value. But that was the one thing that I've noticed, and I noticed that as people are approaching this for the first time, like trying to figure out how this buckling load relates to like that critical failure. And wait, why does this say under that? Because this is just using the geometry of the load. It's not giving you anything about like, is this the actual, when I apply the load, will it buckle? You have to do that comparison kind of after the fact. Yeah. Cool. All right. So keep up the great work. We are working hard on module 2, going into the project, looking at some stock exchange data. And again, if you're running this on your own computer, make sure that you actually get this data. Like you can go into the repository and download it, and then go from there. But yeah. Anyway, if it's saying like, hey, this file's not found, then you have to go find the file and put it in the right place in order for it to call it, like get it loaded up. Okay, cool. Looking forward to your analysis. Make sure you take some time. So a lot of this is kind of like cooking show, like the model is kind of built specifically, and you can change some data to make it work for you. So make sure you take some time to think about, like, what is this method actually telling you? Make a real prediction. So what is your actual quantitative prediction? And then caveats, like what are some quantitative measures? Like, is this an accurate method? Is it a precise method? Like, think about those kind of things as you're doing this project, and make sure you make that clear of like how precise, how accurate, and these kind of things. All right, looking forward to it, and I'll see you next time.